Now let us consider for a moment what these results in this exercise actually mean. Now, first of all, we're asked to show that u and v are characterized by the ordinary differential equations 1 and 2 that I have already kind of marked out over here. Let me just erase this so that it doesn't get confusing. So what do we mean by differential equations? Well, a differential equation is an equation that tells you how the derivatives of something relate to that something. So how the derivatives of a function relate to that function. And what we see here, if we just focus on the first case where we consider u, what this differential equation is telling us is the change of u when the time changes a little bit, the change there is in u is given by the interest that is accumulated at that small time point, plus the contribution that goes in at that time point, minus the benefit that goes out at that time point. And it sort of makes sense, actually. It's actually not that weird when you rethink about it. So if you think about a savings account, that's the way I prefer to think of u, a savings account at the bank. So u of t is the value of, that's the number that denotes how much money is in your savings account at time t. So how does this change at any given time? Well, the money that's in there already accumulates interest. It accumulates continuous interest, and that interest rate is given by delta. So that makes sense. It grows by an interest delta times u of t. And apart from that, there is a contribution rate of c. So at any given time point, the change in u of t is, it also increases with c of t. And also, there's the withdrawal benefit b of t. So this kind of makes sense. And also the condition here that u of 0 should be 0, well, let's think about it. If all the contributions and benefits are continuous, then at time 0, we haven't accumulated any contributions or benefits yet. And when the contract starts, well, everything is just empty. So u of 0 equals 0 is a rather, well, it seems like a fair assumption to make. So just based on an intuitive sense, this sort of makes sense. And you can try to make the same argument for yourself in the v of t case, but with future liabilities instead. Okay, now how do we intuitively interpret the next step? Show that u of n is equal to 0 if and only if v of 0 is equal to 0. Well, the way we can understand this equivalence is this. First of all, it's useful because if it's hard to show that this is true, then you can just show that v of 0 equals to 0 instead. And that might be nice. So if u of n equals 0, what does that mean? That means that when you consider all of the past contributions and benefits, when you consider all of them at the point the contract closes, then they all even out to 0. That's nice. Well, that should be equivalent to the fact that when we stand at time 0, then the future liabilities, that when we stand at time 0, then all the future benefits and the future contributions, when we discount them all back to here, then they also even out. It would be kind of weird if they even out when we accumulate going in this direction towards n, but when we discount the things, they don't even out. So this seems like something that's quite fair to try to show. And yeah, so let's look at number 3. Number 3 tells us that if the fairness criterion is satisfied, so if either u of n is 0 or v of 0 is 0, then we may conclude that no matter which time point t we're standing at, so if I have a timeline here, then no matter which time point t I'm standing at, if I look at my future liabilities, v of t, so if I look at the present value of my future liabilities, that's v of t, then it is equal to the past value, to the present value of my past net contributions. And it kind of all figures into the whole evening out philosophy, because if 3 doesn't hold, then it's kind of hard to imagine how the payments could even out. But there's a bit of math there that we should probably do first. But this is the intuition behind the 3 things that we're asked to show in this exercise.